All right, welcome back. My name is Clayton. We're going to go through the Lewis structures quiz practice problems right now. So question number 1, how many bonds would each of the following nonmetals prefer to make in order to fill its valence shell? So that word prefer is a little bit interesting there. Basically, for instance, nitrogen, it can make 4 bonds, and it does so normally or regularly, right? But if it has 4 bonds, it has a +1 formal charge. So it would prefer to make 3. It only wants to share 3 electrons. It can share 4, but it would rather just share 3. So that's what I mean by prefer. And we can really just look at the periodic table to solve these problems. Chlorine is in group 7. So it has, 1, 2, 3, 4, 5, 6, 7 electrons around it already. If it needs to fill its valence shell, it shares 1 electron. So it would want to make 1 bond with something else, so that would fill its shell. Carbon is in group 4. It has 4 valence electrons, so it needs to share 4 times with something, anything, to fill that shell. So hopefully you're seeing a pattern here. Sulfur is in group 6. 1, 2, 3, 4, 5, 6. Should have done that better. So here we need to share twice, or we prefer to make 2 bonds. Now, notably, sulfur is in the 3rd period, so it can actually have a total of 6 bonds around it. But again, that's an expanded octet. This is pretty simple here. We're looking for just simply how many bonds would it like to make based on its valence structure. Neon is a noble gas. It has a full valence shell already, so it doesn't want to bond with anyone. Hydrogen only has 1 valence electron, but it's in the 1st period. First period only contains an s orbital, and to fill an s orbital, we require 2 electrons. So it only really needs to share 1 time. So it would make 1 bond. And we just talked about nitrogen. I should probably look at these questions before I start answering them. But here, again, we would prefer to make 3 bonds. This guy's already happy right here. And 3 bonds fills our shell. So that's the reasoning. And really, again, all you got to do is look at the group number. This is in group 5. How many does it need to share? Well, 3 gives it its 8, right? So we're trying to get that full valence shell. 1 plus 1 gives it its full duet here, right? All right, cool. That's number 1. We'll move on to number 2. Okay, number 2, indicate the number of valence electrons each compound contains. All right, so in this, all we have to do here is add together the group numbers. So carbon, that's 4. Chlorine, that is 7. Fluorine, that is 7. But I have 3 chlorine, so this would be 7 times 3. So we have 4 plus 21 plus 7, 28, that's 32. Boom. All right. CH3, COOH. All right, so this is 4. This is 1 times 3 for hydrogen, so that's plus 3, plus another 4. Oxygen, plus 6, another oxygen, plus 6, another hydrogen, plus 1. All right, so that's probably the worst way to do that. There's 10, there's 20, there's 4. So that's 24 total. SO2. I know all of these are in group 6, so that's 6 times 3, and that's 18. We're done there. And CO2, this is in group 4. That's in group 6 times 2, so 12 plus 4 gives us 16. All right, pretty straightforward. Let's keep on pushing here. Okay, question 3. Which atom in each of the following compounds would make the best central atom in a Lewis structure? Letter A, a compound containing sulfur, 4 oxygens, and 2 hydrogens. All right, so I know that hydrogen is a very crappy central atom because it can only have 1 bond. Otherwise here, we're looking, generally speaking, for the least electronegative. So that would be sulfur. So sulfur in this one makes the best central atom? A compound containing a hydrogen, a nitrogen, and a carbon. So here I have hydrogen, nitrogen, and carbon. So once again, I know that hydrogen, very poor answer. Between these two, generally speaking, carbon is going to be our central atom. It is less electronegative. And it also likes to have 4 bonds, while nitrogen only likes 3. So, that's another thing to just keep in mind, Carbon also happens to prefer more bonds, so it makes a very good central atom. Our carbon containing 2 chlorines and a xenon. All right, xenon is a noble gas, so we would expect that wouldn't want any bonds. So we have a xenon and 2 chlorines. But this thing is so big, it's in the 5th period. Is that right? Yeah, 5th period. And so with all these electrons so far away from it, they're looking for happiness somewhere else. They're looking maybe for another atom to share it with a bond with. And so I would and I know chlorine, even though it could also potentially have an expanded octet, we know chlorine looks like this. And really it wants to share once. And so in this case, we would expect xenon to be the central atom here. We know chlorine only wants 1 bond. So that's a little bit of a tougher one. A compound containing a chlorine, a hydrogen, and an oxygen. Okay, so in this case, I intentionally put this one on here because it kind of bucks the rules a little bit. What we're looking at here is our electron structure. We have a chlorine. It wants 1 bond. It's in group 7. We have a hydrogen. Those are always ruled out because it can only have 1 bond. Chlorine could have more bonds, but it wants 1 bond. It prefers 1 bond. And now we have an oxygen that wants 2 bonds. Well, perfect. I got 2 things that want 1 bond, 1 thing that wants 2 bonds. So there we go. What's our central atom? It's going to be the oxygen there. So it is not the least electronegative atom in here. It's the one that makes the most sense based on its electronic structure. All right, so that's question 3. Number 4, select the best Lewis structure for the compound with the following atoms. So we have 2 nitrogens, we have 1 carbon, 1 oxygen, and 4 hydrogens. All right, so in this case, all I'm going to do is just build a Lewis structure based on, what we know about how these atoms like to operate. Just looking at them, carbon is the least electronegative and prefers the most bonds. So I'm going to just slap that right in the middle. Now we can go in several directions. I know carbon is going to want 4 bonds. I know nitrogen wants to have 3 bonds. I know oxygen wants to have 2 bonds. And so when I'm making this thing, my goal here is to make everybody as happy as they possibly can be. If oxygen doesn't have 2 bonds and 2 lone pairs, it has some kind of formal charge. I don't want it to have a formal charge. And so let's see here. I'm going to try some things, see if this works. All right, so this is our skeleton structure. I'm just going to be putting this together. Really, I should count all our electrons. So this is 5 times 2, so that's 10 plus 4 plus 6 plus 4. So 10, 10, so this is 24 electrons total. So that's good to know. We need to know that. And here I'm just trying to put together some skeleton structure. There's an oxygen with 2 bonds right there. Carbon has its 4 bonds. Nitrogen, what I got? I have 2 hydrogens left over. So I guess if I put 1 there and there, and a lone pair, then here, fill out all my octets. Let's just count our electrons first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, I'm an idiot. 12 times 2. So that's 24. Okay. All right. But the problem now is look look at this. Look at this nitrogen. That is outrageous. That's not going to happen. So we know this is not a good Lewis structure. So let's try again. We want everybody to be happy. So I'm going to put the carbon in the middle again. Let's see. Let's try nitrogen, nitrogen. And I got 4 oxygens here. So I'm thinking maybe, sorry, I circled hydrogens instead of oxygens. 4 hydrogens here. So maybe if I do this, that makes sense. And then I'll just put my O here. So now I have all my nitrogens, they have 3 bonds. Carbon doesn't have all its stuff yet, but we'll sort that out later. Well, that was dumb. So now let's go ahead and fill our octets. We have, we need 3 there, and so that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 20. That's 24 electrons, but we have a small problem because our carbon doesn't have a filled octet. So what do? We probably make a pi bond. So I'm going to take these electrons and move them into a pi bond right here. And sure enough, let's count our electrons again. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. Okay, so there's our 24 electrons, and everybody seems to be relatively happy as far as the number of electrons that it has around it, or number of bonds, I should say, right? We have both nitrogens have 3 bonds, carbon has 4 bonds, oxygen has 2 bonds. That's perfect. If I were to just check all the formal charges on these, I would get 0 across the board. So that is our ideal Lewis structure for this compound. And incidentally, this is urea. It's something your body uses, or actually something your body throws away. Okay, question number 5. Okay, question number 5. Indicate the formal charge on the following atoms from the given compound. Answer using an integer, blah, blah, blah. Okay. Indicate the positive negative sign. Alrighty. So here, this is actually one of the incorrect answers from question number 4. And looks like we're going to start with nitrogen. These nitrogens are equivalent, so I can choose either one and I'll get the same thing. Why are they equivalent? Because they both have 3 bonds and a lone pair. So when we're doing formal charge, we know that formal charge equals valence electrons minus, I just call them like given electrons, equals our formal charge. And so what does given mean? Well, we'll talk about that. So the nitrogen, it comes to the table, it's in group 5, it comes with 5 valence electrons. Now how many electrons did I give it? I gave it, well, it's got a lone pair right there. That's a bad color, sorry about that. So we got a lone pair, so it gets 2, and then it gets half of each one of these bonds. If we cut each one of those bonds in half, that's 1 electron from each bond. So 2 plus 3, that's 5 electrons, so 5 minus 5, that's 0. The formal charge on nitrogen is 0. Let's look at our oxygen. Sorry, carbon is next. Carbon, it came with 4 electrons because it is in group 4. That's how many valence electrons it has. I gave it 2, 4. That's 1 electron for carbon and another electron for carbon, so that's 6. 4 minus 6, that is a -2 formal charge. And this helps us to see why this particular Lewis structure is so ridiculous. It can't be correct because look at this crazy separation of charges that we're about to have. Let's go ahead and do our oxygen now. Oxygen, it's in group 6, comes to the table with 6 electrons. I gave it 1, 2, 3, 4 bonds. So we chop those bonds in half and it gets 1 electron from each bond. So that's 4 electrons. That is a +2 formal charge. So again, look at the crazy charge separation between these here. And then hydrogen, finally, it's got 1 bond. It comes to the table with 1 electron. It gets half of that bond, so minus 1 electron equals 0. Hydrogen appears to be happy. 0 formal charge. Okay, thank you for tuning in. Hopefully this was helpful, and just keep an eye out for the next one. Thank you. My name is Clayton. See ya.